In this lesson, we're going to study differentials. Differentials are used to determine how a change in one variable will affect the change in another variable. So to begin, let's consider the following graph. So here we have the graph of a function. The blue curve here is the graph of just some function f of x. Down here we have x on the x-axis and the corresponding function value on the y-axis. Now suppose that we change from x to x plus delta x. We want to consider how the function f of x changes. So this distance from here to here is our change in x, or right here. That is our change in x right there. Now the distance from here to here, that is our change in f. So we can label that over here. This distance, we'll call that our change in f, and that is equal to f of x plus delta x minus f of x. Alright, so that's our change in f. Now consider this tangent line right here. This tangent line is passing through the point x f of x. The slope of this line is equal to the derivative of our function at x. So that will be simply f prime of x. So this distance right here, that is going to be f prime of x times our change in x. If you don't see that, suppose we call this distance h right here. Well, notice h over delta x, that's equal to the slope of the line, right? So multiplying the delta x over, you see we get that this h is equal to delta x times f prime of x. So what we get here is this distance from here to here is simply f prime of x times our change in x. And we also have a little distance up here that we will call an error, and we'll just label that with the letter E for error. Now notice that we can approximate our change in f, which is the distance from here to here, with this value, f prime of x times delta x. So we have that our change in f is approximately f prime of x times delta x. And that is a formula that we will use. And notice also that as we let delta x get smaller, this point will move towards x, of course. And notice how the error E, that would be the distance from here to here, that is actually getting smaller and smaller as the delta x approaches 0 and this point approaches x along the x-axis. So as delta x goes to 0, this approximation here becomes better and better. It becomes equality eventually. Now notice one other thing. If we replace the delta f, the change in f, with this number minus this number, what we get is so we obtain this because this quantity right here, that is our change in f. Now if we move the f of x over to the other side, we get another approximation that is useful to us. We get and this is another formula that we will use from time to time as well. So those are some approximations that we get by considering the graph of a function and its tangent line at a particular point. Now we have these approximations listed below, and let's take note of their relationship to the limit definition of the derivative. Now here's our first approximation we developed. The change in f is approximately f prime of x times the change in x. And notice one thing about this: if we were to divide the delta x underneath the change in f, we would obtain this, which makes sense because by the limit definition of the derivative, the limit as delta x approaches 0 of this quantity right here, that's equal to the limit of, as delta x approaches 0, of the change in f over the change in x. You see the numerator right here. That is our change in f. So we have it listed right here. And this quantity right here is our derivative, df dx. So you see what we're saying here is that because of this limit definition, this quantity right here is approaching f prime of x as delta x approaches 0. So this is getting closer and closer to f prime. So that means that delta f over delta x is approximately f prime of x. And that's where this approximation is coming from by multiplying the delta x to the other side. So in other words, this approximation is actually coming from our limit definition for the derivative. Now notice we have this quantity right here, and we can actually write that as, so if we start out with this, we can think of multiplying the dx to the other side, and we get df equals f prime of x dx, where the approximation has become equality now. Now you don't really think of these as being numbers. These are really more like concepts. They're infinitely small quantities. So, but we think of this approximation up here becoming this as delta x approaches 0. So you'll see this written oftentimes, and we have that labeled down here as well. So right here is df equals f prime of x dx. And down here is our other inequality that we had developed earlier that we'll use. F of x plus delta x is approximately f of x plus f prime of x times delta x. And that's coming from the fact that our change in f is exactly equal to f of x plus delta x minus f of x. And then you just take the f of x over to the other side here, and you obtain this. Now let's take a look at a few examples where we use these approximations. For this example, we're given the function y equals x squared plus x plus 2, and we want to approximate the change in y as x changes from 2 to 2.01. So we're going to use this formula. Now we don't have an f up here, we have a y instead. Well, this is just equivalent to so we just replace the letter f with the letter y. Same approximation. Now we want to approximate the change in y as x varies from 2 to 2.01. So let's note that x starts at 2, And as x goes from 2 to 2.1, then the change in x is going to be the ending location, 2.01, minus where x started, which was 2. And of course, in this case, we get 0.01. Now we just have to plug this information into the right-hand side, and that will give us an approximation to the change in y. Now let's also note that y prime is equal to 2x plus 1, and now we can plug all of our information in. So the right-hand side, that's going to equal and y prime of 2, putting 2 in here for x, we get back 5. And 5 times 0.01, of course, is 0.05. So that's our approximation to the change in y. Now, we can calculate the exact change of y in this case. Let's note that the exact change in y is going to be so we're just evaluating y of 2.01 minus y of 2. This will give us the exact change in y as x goes from 2 to 2.01. And putting 2.01 in for x up here, we get, and then y of 2, putting 2 up in here for x, we get 8. And of course this evaluates out to and so here is the exact change in y as x changes from 2 to 2.01. And notice that our approximation is very close to the exact change in y. Now let's take a look at another example. So here we have a ball bearing manufacturer makes ball bearings that are supposed to have a radius of 0.8 inches. The manufacturing process has an error of plus or minus 0.01 inches. So we want to do two things. Estimate the error in the volume of the ball bearings using differentials, and then estimate the percent error in the volume using differentials. So for part A, we want to estimate the error in the volume. Well, we need a volume formula. Well, recall that the volume of a sphere of radius r is 4/3 pi r cubed. That's a formula from geometry for the volume of a sphere of radius r, and a ball bearing is a sphere. Now we want to estimate the error in the volume of the ball bearing, so we want to estimate or approximate our error in the volume given that our radius r is 0.8, and our change in r is plus and minus 0.01. Now using our approximation formula, our change in v is going to be approximately v prime of r times our change in r. We have to evaluate the derivative of this and then just plug our numbers in. So this is equal to, differentiating this, we have to drop the 3 down. That's going to cancel with this 3. We get 4 pi r squared. There's our derivative, that's v prime of r, times our change in r. And now v prime, when r is 0.8 and our change in r is plus or minus 0.01, is going to be, so therefore change in v is going to be approximately 4 pi times 0.8 squared times plus or minus 0.01. Now remember, this doesn't mean adding or subtracting here. This plus or minus really gets pulled out in front of the 4. This means this whole quantity times positive 0.01 or negative 0.01. So evaluating this, you're going to get plus or minus. We'll pull that plus or minus out front, and then evaluating the rest of this on our calculator, we'll get 0.0804, rounding to 4 decimal places. And just take note of something. If you did evaluate V of 0.81, that's 0.8 plus the positive error, 0.01, minus V of 0.8. So this will give you your actual change in volume, your maximal change in volume. You will get 0.0814, which is very close to this number right here. And if you evaluated V of 0.79 minus V of 0.8, you would get negative 0.0794, and this is also very close to negative 0.0804. Now let's take a look at part B, where we want to estimate the percent error in the volume using differentials. For part B, our percent error is equal to our change in volume divided by the volume that we want times 100%. So this is what we need to approximate. Now, to see why this is true, for example, if I asked you 5 is what percent of 80? So the number 5 is what percent of 80? Well, you would evaluate 5 divided by 80 and then multiply that by 100 to turn it into a percent. And this comes out to 6.25%. So we're asking up here, what is the percent error in the volume? So we take the error in our volume, divide it by the volume we want, and then multiply by 100. Just like, thinking of the 5 as being our error, 80 being what we want, and then taking 5 over 80, delta V over V times 100%. Alright, so now this is what we want to approximate, so let's do that. So from our result up here, the change in volume is approximately V prime times the change in R. So this will be approximately times 100%. Now we just have to plug everything in. V prime is 4 pi r squared times the change in R divided by, and V is 4/3 pi r cubed. And then we have to multiply that by 100%. And all of this simplifies. Let's see, the r squared cancels with an r cubed down here, leaving us with 1r. The pi's cancel, the 4's cancel, and we end up with the change in r divided by r over 3 times 100%. And all of that, this is equal to, let's flip this fraction, flip it up and write it as 3 times the change in r over r times 100%. Now let's plug in the change in r is plus and minus 0.01 up here. That's what we're given. And r is supposed to equal 0.08. I'm sorry, 0.8. 0.8. So we plug this and this in here, and we get that this is going to be plus and minus 3 times 0.01 divided by 0.8 times 100%, and evaluating that on our calculator, that comes out to be plus or minus 3.75%. So that's our approximation to our percent error. It's good to calculate a percent error, because if you look back at the number for our actual error, this was our approximation right here, you really don't have any idea if this is good or bad. For example, if the volume of the ball bearing is supposed to be 0.16, well then this is about 50% of that, so your error in your volume can vary as much as 50%. That would not be good. But if the volume is supposed to be, say, 10, then 0.08 is not a large percentage of 10, and so that might be good in your manufacturing process. So we found out that our percent error is approximately 3.75% plus or minus, which isn't too bad. So sometimes evaluating the percent error in a process is a little more meaningful than just evaluating the error. In this example, we want to use differentials to approximate the square root of 16.4. Now we're going to use this form for our differential approximation. So this is the approximation that we're going to use for this problem. Now notice that in looking at the square root of 16.4, we can easily evaluate the square root of 16. That's just 4, and that's very close to 16.4. So notice that the square root of 16 is 4. So using this formula up here, if we think of letting the x be 16 and the delta x be 0.4, and our function f of x is going to be the square root of x, then we'll be able to use the right-hand side here as an approximation to the square root of 16.4. So let's evaluate the right-hand side here. Now we do have to take the derivative of this function. Well, notice that the derivative of the square root of x, which is x to the 1/2, recall that that is 1 over 2 times the square root of x. So now evaluating the right-hand side, we're going to get, now note that the left-hand side, that's going to be f of 16 plus 0.4, and that is the square root of 16.4. And that is going to be approximately f of 16, which is the square root of 16, which we can evaluate easily, plus f prime of 16, so that's going to be 1 over 2 times the square root of 16, times delta x, which is 0.4 in this case. And now, evaluating the right-hand side here, we get 4, 1 over 2 times the square root of 16, which is 4, so 1 over 8, times 0.4, which is 4 over 10. And all of this simplifies to 4 plus, this will simplify to 1 over 20, and we get 4.05. And so that is our approximation to the square root of 16.4. And we can check out how good our approximation is. We can evaluate the square root of 16.4 on a calculator. And so just using a calculator here, if we evaluate square root of 16.4, we get 4.04969, and yes, that is very close to our approximation of 4.05. Now here's an example you can try. Why don't you try using differentials to approximate the cube root of 26.5. Now, assuming that you've done that, I'm going to go over the answer. So once again, we're going to use this. And now, is there a number that is close to 26.5 which we do know the cube root of? Well, yes, that's going to be 27. So we're going to let x be 27. Then delta x will have to be negative 0.5. And our function f of x will be the cube root of x. And then our derivative, we're going to need that, f prime, that's going to be 1 over 3x to the 2/3 power. That's what you get when you differentiate x to the 1/3, dropping the 1/3 down, and then when you subtract 1, you get x to the negative 2/3, or 1 over x to the positive 2/3. So now plugging everything in here, then we get that the cube root of 26.5, that's our left-hand side here, that is going to be approximately f of x, where x is 27, so that will be the cube root of 27, plus f prime of 27, so we plug 27 in here and we get times, and our delta x is negative 1/2. And now let's see if we can evaluate everything here. Well, yeah, this is going to be pretty easy. The cube root of 27 is 3. That's a times right there. Now, what is 27 to the 2/3? Well, 27 to the 2/3, of course, you have to think of that as 27 to the 1/3 power squared. So that's going to be 3 squared, or 9. So we get here 3 times 9 times negative 1/2, and we end up with 3 minus 1 over 2 times 9 times 3 is 27. So this is going to be 3 minus 1 over 54. And we can evaluate that on a calculator to get a decimal form. And we get 2.9814, and that keeps repeating, or 2.9815 if we want to round it. And let's see how close that is to our actual value of the cube root of 26.5 just using a calculator. If we evaluate 26.5 raised to the 1/3 power, we get from our calculator 2.981365,979, and we see that is very close to what we found as an approximation, 2.9814. So we see that our first difference is at the 4th decimal place. So this is a pretty good approximation here. And that concludes our discussion of differentials.